So we're going to move on to waves and their properties. So first of all, what is a wave? Well, waves are disturbances that transfer energy through a medium. You can think about them as like energy transportation services. So much like a bus transports people to work, well, waves transport energy from one object to another. They occur in various forms in nature and technology. Some of the most notable forms are light and sound. But water waves are an example, sound waves and light waves, as we previously mentioned. There are two main types of waves, or two categories of waves that each of those waves fall into. You have transverse waves in which the particles move perpendicular to the wave direction. So an example of this would be light waves or water waves. And then you have longitudinal waves, where the particles move parallel to the wave direction. So if I look at the diagram over here, in the transverse wave, the wave itself, or the slinky, is being shaken up and down while the pulse moves left to right. In the longitudinal wave, it is being shaken left to right while the pulse also moves left to right. So it's parallel. Now, how does a wave actually look, whether it's longitudinal or transverse? We'll explain the diagram on the left here in a second, but there are key parts to, if we're zoning in on a transverse wave here. You have the crest, which are the very top parts of the wave. It's the highest point of the wave. You have a trough, which is the lowest point of the wave. Then you have your amplitude, which is, you can think about it as the height or the midline for the wave. So the distance from the equilibrium to the crest or the trough. So the trough, it should be noted, is simply the inverse of the crest. So if the crest has a value of 3, your trough is -3, but they're absolute values. And we measure those values relative to the equilibrium line or the midline, if you're thinking about it like a sine function. And then you have the wavelength. So that would be the measurement from one crest to the next crest, or one trough to the next trough. Another important aspect of wave propagation is period and or frequency. And so period is the time that it takes for one complete cycle past a fixed point, or from a point source, we could say. And it's typically measured in seconds. And frequency is the number of wave cycles that can pass a fixed point per second. So how many waves, like crest to crest or trough to trough, can pass in the span of a second. These are measured in hertz. And one thing we should know is that period and frequencies are inverses of each other. Another property of waves is how fast they travel or complete their cycles. So wave speed can be defined as how fast the wave travels through a medium, and that same wave pulse might travel faster or slower depending on the medium that it's going through. So the medium is as important as the nature of the wave itself. We calculate your wave speed using the universal wave equation, where it's v, representing the speed of the wave, is equal to lambda, or the wavelength in meters, multiplied by the frequency in hertz, or the speed of the wave is equal to the wavelength, lambda, over the period, so divided by the period. And the speed is in meters per second, the wavelength is in meters, frequency is in hertz, and the period is in seconds. So let's say we have this question here. If a wave, has a wavelength of 2 meters and a frequency of hertz, what is its speed? Well, given that we have the measurement in hertz, we're going to use the first universal wave equation. So V is going to be equal to 2 meters times hertz, and that's going to give us 10 meters per second. So let's look at another wave equation here. at the intermediate level. So sound travels at approximately 343 meters per second in air at room temperature. If a sound wave has a frequency of 440 hertz, which is equivalent to the musical note A, what is its wavelength? So we're solving for lambda. So I'm going to rearrange the universal wave equation in order to get lambda. And when I do that, I should get lambda is equal to the velocity over the frequency. Then I just plug in the numbers, and I get 343 meters per second over 440 hertz, and that gives me 0.78 meters. And so that would be the wavelength. And that is congruent with the number of significant digits that are given, because from the 440 hertz, we have 2 significant digits there. So for this question, a hiker shouts toward a vertical cliff 685 meters away. The echo is heard 4.00 seconds later. What is the speed of the sound of the hiker's voice in the air? So, a couple of things here. We could use, remember that your universal wave equation is your wavelength multiplied by your frequency, which is also equal to wavelength over your period, which, since it is a speed formula, is essentially equal to d over t. So we have 3 ways that this formula can be expressed here. Now, in the context of this question, we have a distance given and a time. Now, if we're thinking about somebody that makes a noise here, right, and it goes to the cliff, but in order for your ears to hear it, it must go here and then back. So your sound actually ends up traveling double the distance. So that 685 is going to have to be multiplied by 2. So when we plug it in here, we're going to go V is equal to 685 times 2 for the back and forth total distance. And then it's heard 4.00 seconds later. When we take that and we plug it in, we get a speed of about 343 meters per second. And in air, that is quite a standard speed of sound. Finally, let's look at a more multi-step, advanced level type of question. So we got a radio station that broadcasts at 98.5 megahertz, and the signal travels at the speed of light, which is about 3 times 10 to the 8 meters per second. Calculate the wavelength of the radio waves. And then B, if this wave passes a fixed point, or a point source, how many wave crests would pass in 1 microsecond? Now this part is the harder part. So for the first part of this question, for A, what we're going to do is we're going to go from megahertz to hertz. And to do that, what we're going to do is we're going to multiply by 1 million, because there is 10 to the 6 hertz in a megahertz. So we're going to multiply by 10 to the 6. So that means that this is going to be 98.5 multiplied by 10 to the 6. And then what I could just rewrite this as is 9.85 times 10 to the 7 hertz. And then with that in mind, I can just rearrange our universal wave equation here to calculate the wavelength. So if I divide both sides by my frequency, then the wavelength is going to be equal to the speed over the frequency. And then, of course, substituting this in, we got 3 times 10 to the 8 meters per second divided by 9.85 times 10 to the 7 hertz. And that gives me about 3.05 hertz. And of course, we want, based on what's given here, we want 1 significant digit. So we'll just say approximately 3 hertz. And so that would be the answer to the first question over here. Now, for part B, there are 2 things we need to figure out. First of all, we need to figure out how many microseconds are in a second. And the answer is 1 million, right? We say that 1 microsecond is going to be equal to 1 times 10 to the negative 6 seconds. The second thing we're going to have to figure out is, we have the frequency here. Remember what frequency actually means, and that's the number of events that occur over a specific slot of time. So in the context of waves, the number of events would be the number of crests. So I would write number of crests, or waves that pulse through, and that would be divided by the time, or the period in seconds. And so what we could do here is, if that's the case and we have the frequency, then we can go, if I'm thinking about what the number of crests would be, well, I would go the number of crests, so number of crests equals, and then we're going to say that it's the frequency multiplied by the time, right? That's the most appropriate formula over here. And then plugging everything in, and when we plug all of that in, and I'll write that answer in yellow at the very bottom here, that is going to give us about 98.5 crests. And that would be the final answer over here.